what you sent around. Jeremy is an expert in iron and steel making, particularly electric arc furnace steel making, I think. And he's known internationally and nationally, particularly in North America. And he's published many papers in the field. And he's agreed to talk to us tonight, give us an update on a steel making technology. So pass the floor to Jeremy. And thank you for everybody for showing up today. And ask some good questions at the end. That's my advice. Okay, thank you, Jeremy.
So tonight I'm going to talk on steelmaking technology, and it really is just a brief introduction because I could probably talk for a week easily on all the different aspects of this. But my background is I'm a low temperature metallurgist, also known as a chemical engineer. And I graduated from Queens in 1983. So just to put things into perspective, well, what is steel? Steel is the most important engineering construction material in the world. It's technically defined as an alloy of iron and carbon containing less than 2% carbon. There are more than 3,500 different grades of steel. A grade of steel is like a chemical recipe for steel. And over half of the steel grades currently used in automobiles didn't even exist 10 years ago. In 2019, world steel production exceeded 1.8 billion tons. Steel is also the most recycled material in the world. On average, new steel products contain 30% recycled steel. In 2014, 86% of the steel scrap that was generated got recycled. And recycling steel scrap is very, very important environmentally, also in terms of energy and other resources. So for every ton of steel we can recycle, we can save about 2,500 pounds of iron ore, 1,400 pounds of coal, 120 pounds of limestone, and 12 gigajoules of energy. So the main technology focused on recycling steel scrap is the electric furnace, though we actually use up to 30% scrap in what we call the integrated route as well. In North America, we have the highest electric steel making capacity at about 70% of our total steel capacity in North America is based on electric arc furnaces. And that's very important because as we move forward, all of the new initiatives on reducing carbon footprint tend to be focused around the use of electric furnaces as a producer of steel with a very low carbon footprint. To put things into perspective, the cost for scrap is about $1.50 US per kilogram. Actually, that should be, yeah. The price of steel, probably a little more than double that. So what's steel used for? Well, by far the biggest user of steel is building and infrastructure. Second largest use is mechanical equipment, and the third is automotive. But we also have a number of other metal products ranging from containers, tin cans, drums, all sorts of other products. Other transportation other than automotive and, well, ships, bicycles, motorcycles. Electrical equipment and domestic appliances account for a small percentage. So iron ore, well, what's it look like? It's generally a reddish rock, depending on whether it's hematite or magnetite, will affect the shade. Magnetite tends to be a lot darker. And we take that iron ore and we process it and beneficiate it, and probably you've covered some of that in your classes. And we produce iron ore pellets, and these iron ore pellets can then be fed into the steelmaking process. Now, just to give you some additional background. So if we look at a number of different steel products, ranging from rebar, which is used for construction, structural steel, beams, plates, forging steel, and then flat products. And you see some of these listed: drawing, cold heading, fine wire, deep drawing quality, DDQ. DDQ, that's the type of steel you use for panels for a car, where it has to be easy for us to deform, but it also has to be strong. And you can see that the copper, nickel, moly, chrome, and tin levels for these different products, as we move down the list, the requirements are getting a lot more stringent. And why are these elements important? These elements are very important because they're what we call residuals. These are elements that we can't oxidize out of the steel. So in a molten steel bath, if we blow oxygen, there are a number of elements which will be removed. Things like silicon, aluminum, manganese, phosphorus. But if you look at the Ellingham diagram, the oxide stability diagram, what you'll see is that in order to remove copper, nickel, moly, or tin, you would have to essentially remove all of the iron first. And if we removed all of the iron and oxidized it back to iron oxide, we wouldn't be very good steel makers. So what we typically have to do is, if we have to achieve lower levels for certain products, then we have to use some new material that has very, very low residual content in order to make those grades of steel. Chrome is one of these things. It is a residual, but once you get below about a 0.6 carbon content in the steel bath, you can start to oxidize chrome out. And obviously that's very important when you're making things like stainless steel, where you want to keep the chrome in there. This just gives you some idea of different scrap types and the residual levels associated with those. So things like shredded automotive, you can see lower copper content. Things like heavy melt. This is material. Number 2 heavy melt might include rebar. Rebar typically has very high copper contents, above 0.4 weight percent, because it's not necessary to form rebar and bend rebar. You're not really doing a lot of deformation, so the copper has less of an impact. Whereas for flat rolled products, when you're rolling and deforming steel, producing a flat product, copper deforms at a different rate than the iron does. And so what happens is we'll tend to produce tears or holes in the steel as we start to form it if the copper content's too high. That's sort of a simplistic overview of that. So some of the different types of scrap, we have some scrap types which we call prompt scrap. So this is busheling and clips. This is scrap that's generated from recent processing. So basically we take sheets of steel, they go into a manufacturing process, they stamp out parts, and what's left over is called busheling and clips. Frag is basically material that's being shredded, but it tends to be heavier, more dense than your typical shredded scrap. This is shredded scrap here. And we used to refer to this as shredded automotive. Now people are shredding a lot of other grades of scrap as well, which is causing a bit of a problem, because typically shredded automotive scrap only had, you could get it with as low as a 0.12 weight percent copper content. Now it's trending up closer to 0.3, 0.35. And you can see that everything goes into the shredder, and you'll see bits of wire and fluff and other things. And obviously we would prefer if those things were taken out, but nobody's willing to sort of pay the cost to remove some of those materials before the steel scrap gets processed. Plate and structural, yeah, it's just like what it sounds like. It's just demolished industrial buildings. Turnings and borings, these are from recent production as well. When you have components that you're boring or shaping, drilling, then the waste materials that are left over can be used for steel making. Downside of some of these materials is that they sometimes contain a lot of oil. Now, nowadays, a lot of operations are trying to move towards water-soluble lubricants in this type of processing, so that we don't have a lot of oil and grease in these materials, because that does pose a problem when we use them in the furnace. So they're trying to produce materials that are a little cleaner. But unfortunately, because those materials are so small, you have to use them up very, very quickly. You can't leave them standing around for too long. If they're standing out in the rain, after a few days, they'll end up looking like this. Bundles are just your typical sheet scrap that is just being put through a process to basically compress it, make it easier to handle and easier to transport. These are called bundles. And so you can see in the scrap, we sometimes have other materials. We can have dirt, we can have all sorts of fluff from automobiles. So it's not entirely pure. And sometimes when you're processing sheet steel, they use a lubricant on it. And that lubricant, though it's not very much, it's on the surface, and it's a light oil. And so if this scrap sits around and you have dry conditions with dust blowing around, the dust will eventually cake. It'll stick to the oil on this scrap and again, contaminate the scrap. And sometimes the scrap like tire cord. So this was a plant in South Carolina. And it was quite interesting because they used a lot of tire wire. So it's tire cord, it's the wire from your tires. And they shred the tires and they recover the tire cord. But you can see this is on the left here, you can see material that was just delivered. And on the right, you see material that sat for 2 or 3 days. And so again, you have to use it very, very quickly, or you'll take a lot of yield losses. And when this oxidizes, it takes a lot of energy as well as a reductant like carbon to try to recover that iron oxide and get it back as metallic iron in the steel bath. So those are some of the challenges we're facing. And when I talked earlier, I said, well, sometimes we've got to add some cleaner materials that have low residuals. So these would be materials like DRI, direct reduced iron, and HBI, which is hot briquetted iron. It's just basically these same pellets taken while they're still hot. They come out of the process reactor and go directly into a briquetting machine, and they make these nice briquettes. And because these materials are based on iron ore, then they have very, very low contaminants with respect to residuals. And so we can add this material along with other steel scrap that we want to recycle that has a higher residual content and still meet the requirements for higher quality products that require very low residuals. This just gives you a few photos. And the other thing that we'll use sometimes is pig iron. So this is Pig iron that's being produced by the integrated route, usually in a blast furnace or in a what we call a mini blast furnace, which is similar to the blast furnace, but it operates with charcoal instead of coke. And sometimes they'll pig this material and they'll use this as a charge material for the electric arc furnace. And again, this typically contains 4.3 to 4.5% carbon, anywhere from 0.1 to 1.1% silicon, maybe 0.3 to 0.5% manganese. But other than that, it has very, very low copper, nickel, moly, and tin content. So I just put a few tables in here. These are all from an organization called World Steel. And if you're interested, you can go in. They have lots of free material you can download. But it just basically shows the world production of steel from 1950 up to 2019. And what you can see is that up to 2000, we were producing about 850 million tons a year of steel. And then what happened was we saw a huge increase in steelmaking output, and most of that was installed in China. So China produces a huge amount of steel. So in 2019, 996 million tons. So basically, more than half of the world's steel is produced in China. You can see here, United States, now about 88 million, and Canada's at 13 million. But the two countries that are really growing in steelmaking capacity are China and India. Japan's starting to shrink back. The US used to produce more than 100 million tons just 20 years ago, but they've cut back quite a lot. And they import steel now. And then we see Russia and South Korea, Germany. And this is just a table to give you an idea of the world trade in iron ore. So most of the world's iron ore is actually mined in Brazil and Australia. So those are the two largest producers of iron ore. And it's shipped all over the world. And in fact, China imports probably about 80 to 90% of the iron ore that they actually use comes from outside of China, a lot of it from Australia. And then this just gives you an idea of world steel exports, again, from 2014 to 2019, and just has a number of different products all broken out. And I think it's always important. So this is a very interesting graph, because what it shows is the per capita use of steel in kilograms of finished steel equivalent. And what you see is that the largest per capita use of steel is in South Korea. And this is kind of interesting. Canada's right up there, very, very high. So that's a bit of an indication that Canada is still growing and developing their infrastructure. And as you saw, two of the major uses of steel were related to infrastructure and construction. And then you see, a lot of the countries in Europe are fairly well developed. They're still obviously using a lot of steel, but not as much as Canada, China. So steelmaking processing, as I said, the two main processing routes are integrated steelmaking and electric arc furnace steelmaking, EAF steelmaking. So if we look at the European Union, uh, they're about 60% of their production is based on integrated steelmaking. And they're going through a massive sort of overhaul because in order to reduce the carbon footprint of their steelmaking, they're going to have to transition to a much higher percentage of electric arc furnace steelmaking. You see in NAFTA, we're already pretty far ahead. In the Middle East, there's very little integrated steelmaking. And the reason for this is that a lot of their steelmaking is based on the production of direct reduced iron. Remember those metallic pellets I showed you? I'll explain the process in a few minutes. But so they tended to be electric furnace based. And then we see other areas like Asia, not even 20% electric arc furnace. And that's partially due to not really having the electrical power available in a lot of cases. And this is a problem in China, where they're at about, I think for this past year, they're now up to 12% electric arc furnace based. And then you see the world figures, 28% electric furnace based, but that'll really change. Between now and 2050, you'll probably see that grow to about a 50-50 or maybe even higher. I included a bunch of slides in here on the historical timeline of steel production, but I'm going to leave that for you guys to go through the handouts and basically read up on that. It's very, very interesting, and it helps to put things into perspective, but I'm going to jump ahead just because of time to where we talk more about modern steelmaking processes. So let's see, that'll get us to here. Okay. So as I said, there are two main processing routes to steelmaking. The integrated, which utilizes iron ore and goes through a reduction and smelting stage to produce metallic Fe. And the EAF route, which utilizes recycled steel scrap as feedstock. We can also use things like pig iron, direct reduced iron, if you need to produce products with lower residual requirements. So if we look here, here we see a typical on the left, a typical integrated plant. It utilizes a blast furnace into which we feed coke, lump ore, sinter, or iron ore pellets. And we feed those into this shaft furnace. We blow hot blast, which is hot air, which might be oxygen enriched, into that vessel. And along with pulverized coal, this was a technology developed to reduce the amount of coke required and basically substitute other carbon for the coke. And that allowed people to reduce the amount of coke they were using in the blast furnace by about half. But the coke basically provides not only a metallurgical purpose, but it also provides a structural purpose because it helps to support the burden, all of these materials that you're feeding in to the blast furnace. And out of the blast furnace, you have hot metal or liquid pig iron. As I said, typically 4.3 to 4.5% carbon. And that material gets charged into a BOF. BOF stands for basic oxygen furnace. It's sometimes also called BOS, basic oxygen steelmaking, or a number of other names, which I'll cover in a few minutes here. And what we do is, because we're going to blow this hot metal with oxygen, we're going to remove a lot of carbon. We're going to generate a lot of heat. We're also going to remove silicon, and that generates a lot of heat, the oxidation of silicon. So what this allows us to do is, depending on what the chemistry of our hot metal is, we can make a charge calculation and add scrap. And this scrap helps to soak up all the extra energy that we generate in here as we reduce the carbon and the silicon content of the hot metal and produce steel. So typically in North America, we tend to charge 25 to 30% scrap because of our hot metal chemistry. In some places like China, they were typically around 10, and recently they've increased to about 15% scrap. So there is some steel scrap that gets consumed in the integrated steel process. The second possibility is smelting reduction. And again, there's a process called the Corex process, which was first installed in South Africa. It's a smelting reduction process where they basically feed pellets, lump ore, in some cases fine ore. There's one plant in Korea called POSCO, which is a lot like the National Steel Company in Pohang, and they have a process around the use of iron ore fines, so they don't have to go through the cost of pelletizing. And those materials get fed into this melter gasifier. The top gas comes off and it's very high in CO, so it's used as a reductant to pre-reduce pellets and lump ore before they're fed into the vessel. And the output of this is again hot metal that can go to a BOF, or it could potentially get fed to an electric arc furnace. There are some electric arc furnaces that use liquid hot metal if there is a surplus. Several plants in China actually do this, and they use liquid pig iron up to 50% in the charge to the furnace. Then we have the direct reduction process, which is typically a shaft furnace. And I'm going to cover that in more detail afterwards, but the DRI and HBI that's generated along with steel scrap can be charged to an EAF. And that allows you to produce steel, or you can just use straight steel scrap in an electric arc furnace to produce steel. So in an integrated steel plant, the core of the process are the blast furnace and the converter, the BOF. But you also have these other large facilities, the coking plant, which takes coking coals and basically heats them and drives off all of the volatiles to produce coke, which is charged to the blast furnace. And then you saw that in some cases, people, in addition to pellets and lump ore, are charging what we call sinter. So sinter is basically material that's produced. It's in a furnace. It's kind of like a tunnel furnace. And material gets heated up and it actually sinters together. So what a lot of people do now is they take waste iron products that contain iron oxide along with some iron ore, and they will add that into this furnace and produce this material, which is then broken into smaller pieces after it exits the furnace, and that can get charged as the feed material to the blast furnace. And this is very common in China, and also to a certain extent in Europe. The problem is that this sintering process is one of the dirtiest processes environmentally. So people are trying to move away from that. But people still tend to use it because it's cheaper than pelletizing iron ore and putting that in your blast furnace. So a lot of these decisions are driven by cost, but we expect that might change in the future. So after we go through the converter, or if we melt material in an electric arc furnace, the material then tends to go to what we call a ladle furnace. The ladle furnace is essentially, we tap the steel into a refractory lined bucket. It's a really big bucket, but that's probably the easiest way to describe it is a refractory lined bucket. And we take that and we sit it underneath essentially just what would be an electric arc furnace roof. It's smaller and with a much less powerful transformer. And the whole idea here in the ladle furnace is to carry out reactions that are reducing. So in the EAF, we carry out a lot of oxidation reactions. And then in the ladle furnace, we do things like try to remove sulfur, which is a reducing reaction. It requires that you reduce the oxygen content in the steel, the oxygen content in the slag. And we adjust the temperature. And this unit essentially paces what's happening in the steel shop and then coordinates with, you may go through some vacuum treatment, but in a lot of cases, you go from the ladle furnace to the caster. And at the caster, we basically allow the steel to pour out of the ladle into a big trough. And that trough feeds water-cooled copper molds that help to solidify the steel into a particular shape. And the steel is cast continuously. So as it moves through to this point where it's cut off into specific lengths, the liquid core of the steel is solidifying. And then whether we produce billets, so billets are defined as either square or rectangular shaped cast steel with a dimension of, I think we can go up to 5 by 7 inches, and it's still considered a billet. So they can be square or rectangular. Once we get above 7 inches, if it's square or rectangular, we call it a bloom, or sometimes a round if it's actually cast in a round shape to feed a pipe mill, or sometimes it's cast in these slabs, which go into rolling for the flat products. And whatever the product is, typically it's cooled after it leaves the caster and then put back into a reheat furnace and then into a rolling mill. Though there is a very interesting technology in Europe that my company's worked on, where they go directly from the caster directly into the rolling mill. And it's called the ESP process, and was developed by a gentleman named Mr. Arvetti. Blast furnace steel making, just to give you a little bit more idea. So we feed a lot of raw materials into the blast furnace. Coke, iron ore, limestone, and those typically get moved up a conveyor into skip, falls into hoppers, and then there's distribution here. There's a Paul Worth system that actually rotates and provides better distribution. But as we carry out the smelting of the iron ore in the blast furnace, we end up with gases that are produced. And these gases contain a lot of hydrogen and CO. And so what we do is we tend to collect those, and then we burn those to heat the air that we use to inject into the bottom of the furnace. And this air flows up through the furnace, reacting with the carbon and producing CO. And CO reduces the FeO to metallic iron. And by the time it reaches the bottom here, the metallic iron melts and it collects in the hearth here, and we actually tap off slag and molten iron separately to other vessels that take it to other parts of the plant. Okay. So oxygen steelmaking, the history is that it really didn't have any commercial success until after World War II. There was a top-blowing process utilized at Linz and Donawitz, two plants that were run by voestalpine. And as a result, this was called the LD process. They were typically using ores that were high in manganese, low phosphorus. And in North America, we adapted the process to yield what we call the BOF. We're blowing high purity oxygen onto the surface of the hot metal in a basic line vessel in order to convert the hot metal into steel. There are other variations of the process. There's one called the QBOP, where oxygen is blown into the bottom of the vessel. And we typically shroud the oxygen with natural gas or propane in order to cool it so that it doesn't burn back to the bottom of the vessel. And bottom blowing allows you to move closer to equilibrium between the steel and the slag. And then there are some processes that combine top and bottom blowing. So these are all different variations of the BOF process. Okay. I will skip through that. So the basic steps in the process when you're getting ready to start a cycle to make a batch of steel, the BOF vessel will tilt over. You'll come in with a charging ladle. It's got a lip on it to make it easier to pour hot metal into the vessel and charge it. So you can see that in these two photographs. As I said, the charge in the BOF typically consists of somewhere between 70 and 90% hot metal that comes from the blast furnace. And what we're going to do is remove all of the carbon and the silicon. In doing that, we generate a lot of energy, so we charge 10 to 30% steel scrap to take advantage of that energy. And here you can see a charging container. In BOF shops, they tend to be rectangular, and they're basically pouring, they load scrap in here with a crane somewhere back over here. And then they bring that in with the crane and they pour the scrap into the vessel in order to get ready to start the heat. Now, the main difference when you look at direct reduction, you look at the blast furnace, a lot of the materials that are used are very similar. We're using iron ore pellets. We use a higher grade of iron ore pellet for direct reduction because what we're doing is taking the iron ore and converting it to metallic iron without melting it. So we're doing it while it's still a solid. And we do that by reforming natural gas to produce CO and hydrogen. And that penetrates into the pores of the pellet and removes the oxygen. So it tends to be a cleaner process. And so a lot of people who have blast furnaces are looking at maybe in the future replacing them with direct reduction. And I've got a few slides that I'll show you in a minute. Electric arc furnace steelmaking. The carbon arc was discovered by Sir Humphrey Davy in around 1800. And the practical application for electric furnaces was first really applied by Sir William Siemens, who built furnaces in the late 1800s. These furnaces did not tend to be round, they tended to be rectangular. But the problem at that time was that the availability of electrical power was very limited and also very costly. So even though this was the precursor of electric furnace steelmaking, it really didn't start to get developed until power became more widely available. And then they also improved the quality of the graphite electrodes to supply that energy. So if we look at the electric arc furnace around 1900, it was developed by a guy named Hérault in France. And these early furnaces were actually DC, because at that time that they actually hadn't come up with the concept of AC power yet. So it was a direct arc steelmaking furnace. And the first furnace installed in North America was at a plant called Holcomb Steel in Syracuse, New York. It first produced a heat of steel in 1906. Furnace had a 4-ton capacity. In 1909, a 15-ton furnace was installed at Southworks of Illinois Steel Company. That was the first round furnace. And it used 25 hertz power, 2200 volts. So up until about 1980, nearly all furnaces installed were AC. But over the last 35 years, a lot more DC furnaces have been installed. So essentially here again, we've got our feed materials coming in. We charge them to an electric arc furnace. We melt them. We carry out some oxidation reactions to remove some of the impurities like silicon, some of the manganese, phosphorus. Then we move on to the ladle furnace, where we adjust the chemistry, we do alloying, we adjust the temperature, and we might remove some sulfur. And then that then makes its way to the caster, where it's cast into semi-finished products. So the electric arc furnace is quite interesting. I work a lot with these. This one's an AC furnace. You can see that it has 3 connections, one to each arm from the transformer vault. So this is actually the electrical delta protruding out through the wall of the transformer vault. We use water-cooled flexible cables to connect to the arms. These arms hold electrodes in place, and the electrodes supply power. So because this is 3-phase, what it means is that we're arcing between one electrode, and then the return path for the current is through one of the other 2 electrodes. So we start off to start a heat. This roof actually swings laterally. Whoops. And that allows us then to drop scrap into the shell. And the shell is very interesting. The upper portion is water cooled, and the lower portion that actually provides the containment for the liquid steel is refractory lined. So if we look at this, this would be the lower shell here, and the upper shell is water cooled, and the roof is also water cooled. And so we have these arms, and we have a system using hydraulics to adjust the position of the arms in order to maintain a current set point within the furnace. And as I said, the power is supplied from a transformer, which is contained in the vault. And that transformer will typically have several different voltage taps, because at different stages of the melting, you might want to use more or less voltage. Voltage is essentially the same thing as the equivalent to the length of the arc that you see in the furnace. And the whole concept behind this kind of melting is the concept of joule heating. So what we do is we pass a current from one graphite electrode through the scrap back to another graphite electrode. And as that current passes through the scrap has resistance to the flow of the current, and we end up with joule heating, I squared R. So that's the whole concept in a nutshell behind the electric arc furnace. So here you can see an actual, this is an industrial electric arc furnace from one of my clients. And you see that the electrodes are clamped. We're holding an electrode attached to each of the three arms. We have these masts which can move up and down hydraulically, are used to regulate the power input to the furnace. And the graphite heats up enough that it's glowing white hot. In fact, the temperature in the electric arc itself is probably on the order of 8,000 to 12,000 degrees. Very, very hot. This just shows you the main components again, the furnace bottom, which is refractory lined, and the water cool panels. We also have around the electrodes that protrude through the roof, we tend to have a refractory piece, which is called a refractory delta. And that basically insulates so that we don't arc out directly into the water cool panels. And this just shows you, here you can see this is a plant that's down for maintenance. So they've lifted the water cooled section, the upper shell, clear away from the furnace bottom. And here you see a furnace bottom that's been taken out of service and is being basically relined with refractory patched up. So that top piece just sits right on top of this part of the furnace. And inside the furnace, we use a number of auxiliary systems. One of the main ones is a system to supply chemical energy as well as electrical energy into the furnace. And we have these, they're actually these multi-purpose injectors now, which can act as a burner or they can act as an oxygen lance. And that's what you see here in this photo. So we're basically melting the steel scrap in here once it's all liquid and we've finished removing silicon, phosphorus, and so forth. And it's hot enough and at the desired tap chemistry. And then we're ready to tap the furnace. And what happens is that this whole structure tilts over. Oops, okay, I got ahead of myself. This just shows a DC furnace. In a DC furnace, you have a single graphite electrode and the conductive path back, the return anode, is actually in the bottom of the furnace. And that can consist of steel pins, or it can consist of steel fins. It can consist of conductive refractory, a carbon-based refractory. So there are a number of different types of DC furnace return anode bottoms that are in use. To melt steel scrap, it takes a theoretical minimum of about 300 kilowatt hours per short ton. And then once you provide superheat, because you don't want to tap the steel from the EAF at its liquidus temperature, because as soon as it chills a little bit, it'll start to solidify. So we actually have to provide a sufficient amount of superheat to keep it liquid so that we can continue to process it and then get it to the caster. And then at the caster, we want the metal to go into the copper mold and get cooled to start to solidify. So with superheat, you're typically looking at a total equivalent energy requirement of about 350 to 370 kilowatt hours per ton. But when you look at inefficiencies, and especially when we use a lot of chemical energy, we produce a lot of hot gases. And we can't effectively recover all of the energy from those hot gases. So we have some inefficiencies. So you'll see that the total equivalent energy input in electric furnace steelmaking is typically about 600 to 700 kilowatt hours per ton. This just shows an energy balance from a furnace from say the late 70s, early 80s, comparing it to what we call an ultra high power furnace in the late 80s, early 90s. And you can just see that we got more efficient. But then as we tried to push faster and faster cycle times.
Visiting Henry today?
Sorry, what's that?
Oh, sorry, that was me. No problem.
Oh, I thought you were asking a question. So the EAF cycle, you typically charge scrap to the furnace, you melt it, then you might charge more scrap to the furnace and melt it, and then carry out what we call refining, which is blowing oxygen into it. Take a temperature and a sample to see if we're where we want to be. And then we tap the furnace, and then we turn it around. So we might have to adjust our electrodes and so forth. So here you see the charging process. Furnace is starting to lift the roof, and it's going to swing this roof out of the way so that this bucket can come over and drop scrap in the furnace. Now, the reason why it sometimes takes more than one charge to make a heat of steel is that the bulk density of the scrap might be quite high compared to the bulk density of the liquid steel. So sometimes it takes two, or even in the old days, I worked on one furnace where it took 5 charges of scrap to make one batch of steel. And this was a furnace that was tapping 42 tons of liquid. But it took a lot of work. So the roof swung out of the way now. The scrap bucket's coming in the crane, and they have these cables that are connected. And the bottom opens up like a clamshell and allows the scrap to fall into the furnace. Here again, you see it just swinging back. This gives a good view of the transformer vault and the electrical delta from the transformer protruding through the wall, connected to these water-cooled cables, which are then connected to electrode arms. And here you see, this is a furnace that I worked on in Turkey, where the active power in this furnace tops out around 220 megawatts, which is more than enough to light up a town. This particular furnace produced batches of steel around 330 metric tons. So it's a very big furnace, and it's also the most powerful one in the world right now. So here you see the scrap. You see the clamshell swinging up to the sides, allows the scrap to fall down into the furnace. And then we swing the roof back over and we melt. So once we're done melting, we take a test through, this is called the slag door at the back here. That allows us to tilt back and pour off some of the slag if we desire. And then we might take a temperature, a steel temperature, using a thermocouple probe. And we might also take a sample of the steel and have it tested at the lab. And if we figure, yeah, that's okay to tap and send downstream, well, then we'll tilt the furnace over, and here you can see the front of the furnace. So it's tilting over, and the steel pours out into the refractory line bucket or ladle. Here you see a chute that's used for adding alloys or fluxes into the ladle during tapping. And here you see another furnace tapping. So the ladle is basically refractory lined steel bucket. It uses different types of refractory depending on whether the refractory is likely to contact steel or slag. You can see this area here is identified as the slag line in the white here, just here. In the bottom, you'll see that it's got several openings. So it's got, this one is actually a porous refractory plug called a porous plug, and it's used to introduce gas into the ladle to stir it in order to get good mixing and homogeneity in the ladle. After we add alloys, it's very important to get them well mixed in so that it's homogeneous. And then here you have the nozzle, which the steel, it has a slide gate. And when the slide gate's opened, once this is placed at the caster, the steel pours through this nozzle down into the big trough called the tundish. And we cast the steel. Once the casting is done, the ladle typically has to be cleaned up a little bit. So here you see some people actually working on a ladle, and they'll try to clean up some of the skulls, steel and slag, and clean the porous plug on the bottom so that they won't have difficulty establishing gas flow on the next heat. So this just shows the typical cycle. You have this ladle, you tap into it, gets transported to the ladle furnace, then to the caster. Afterwards, it gets cleaned, then it gets put on a stand where it gets heated. It's called a ladle preheater, which is what you saw right here. So this is basically a panel that's refractory lined on the inside and has a big burner that's used for heating the inside of the ladle. And this just gives you an example of the ladle furnace. Pretty straightforward. So some of the different objectives of various furnace designs were to lower capital cost, lower primary energy consumption, achieve higher productivity or lower conversion costs, flexibility and choice of feed materials, more environmentally friendly, optimized energy use, and tap-to-tap times or cycle times closer to that of a BOF. So a BOF can typically process a heat of steel in anywhere from 25 to 40 minutes. And so that became the goal for electric furnaces. And we have some now that are capable of completely producing a batch of steel in 30 minutes. Probably on average, most people are between 50 and 60 minutes these days. So what we did was we started to develop technologies to recover energy from the waste off gas, to post-combust CO that's generated in the furnace, to CO2 to recover that additional energy, using higher carbon use, which would allow us to input more chemical energy concurrent to the electrical energy input, and then things like maximizing power on time as a percent of the available operating time. So we came up with a number of technologies, which I'll show you in a second. This is just a diagram of a caster. So the steel goes from the ladle into the tundish and then gets poured down into these copper molds, which are water cooled. And so we form a solid shell on the outside of the steel. And then we continue to cool it by spraying water. This is called a spray, the spray chamber. And gradually, as it progresses through the caster, it completely solidifies. So you can see the center line going from liquid eventually to a solid. And then further downstream, it actually gets cut into specific lengths for further processing. Yeah, I think we're good on all those. So I promised to show you guys a little bit about direct reduction. So direct reduction, there are two main processes that dominate the market right now. And they're both shaft furnace technologies. So they take iron oxide pellets. Some of them, some operations use lump, but the problem with lump ore is that it tends to be fragile and you generate a lot of dust, which then gets blown out of the furnace. So you take a yield loss. But if you produce this direct reduced pellet, it can then go directly into these very large briquetting presses and then gets cooled, transferred into a ship and moved somewhere in the world to a steel plant. So the Midrex process is one of the two major processes in use. The Midrex process, what they do is they have a proprietary reformer where you feed natural gas and it's going to basically crack that gas, produce hydrogen and CO, and that's fed into a shaft furnace, and the gas flows countercurrent to iron oxide pellets, which are fed at the top. And then the pellets progress down through the shaft and eventually get discharged. In some cases, the direct reduction plant is right beside the steel plant. And so they feed the material while it's still hot, up to 600 degrees, directly into the electric furnace. Some people also use pneumatic transport, refractory lined containers to transport it, or hot transport conveyors. So there are a lot of different ways. If the direct reduction plant is located adjacent to the steel shop. The other options are to briquette the material to produce HBI, or to put it through cooling, and then you have just cold DR pellets, which you saw in the photograph earlier. I included this just so that you can see all the different reactions that are taking place. I'm not going to go into a lot of detail because I usually spend 2 hours just on this process. So we're not going to do that today. But again, here just pictorially, you can see the DR pellets, the HBI. And this is one of the containers used for hot transport. So what do these look like? Well, it's a very large plant. So a 2 million ton a year plant could cost about $600 million. So it's not an inexpensive technology, but and these towers are several hundred feet high, depending on whether or not there's a briquetting press underneath. That'll typically add to the height of the installation. Okay, the other process is one that's called Energy Iron, and it's a joint venture between two companies, Tenova and Danieli, both Italian companies. And this was kind of interesting in that it can use a reformer, and in some cases, the early installations used a steam reformer to reform natural gas. But most of the time now, they actually do what's called in situ natural gas reforming. So the natural gas is injected into the shaft and actually reacts with the iron ore and cracks to produce hydrogen and CO. So again, I've included this just so that you can see all the different reactions that are taking place. So it's a complex reactor, but it's well established now. Again, the reforming reactions, and then the reduction of the iron ore, and eventually the carburization of the iron. So just to give you an idea, these are really big. So these are people, and this is the reactor vessel being lifted into place at a plant in Egypt. Okay, we can skip that stuff. So how am I doing on time? Okay. I've only got a few more slides, so if you bear with me. Some of the technical challenges in steelmaking now. Well, green steel, trying to decarbonize the production of steel is a major challenge. There's a lot of money being spent on this in Europe right now because they realize that they have to change their steelmaking process route. And a lot of them are considering direct reduction. In fact, they're actually considering direct reduction with hydrogen. So instead of using natural gas, they will actually go through hydrogen electrolysis. So they'll feed water into the electrolytic unit, produce hydrogen, and use that as the reductant in the direct reduction shaft. So a lot of work being done looking at how to solve some of those issues. A lot of changes in energy supply and use, and obviously we want to go to greener options, but we also have to keep things into perspective. So a recent study that I saw, I get these reports from a group called the International Energy Agency, IEA, and they track all sorts of things related to energy. So they did a study in Europe and they said, well, if our electrical demand doesn't change, then we only need 25% of the land mass in Europe to produce energy, either wind or solar. But then as they started to look at a lot of processes that use chemical energy, replacing that with only electrical energy would further double the amount of electrical energy that's required. So now we're looking at in Europe, well, 50% of the land mass would be required for wind farms or solar farms. And part of the problem with that is that the areas that are really good for solar farms are also areas that are really good for growing food. So you don't want to be faced with the option of either eating or having power. Now, one of the big things that happened just this past, well, it was about 6 months ago, some changes in solar technology. A group was able to produce a panel that achieved 39, I think it was 39.7% efficiency, which is like a doubling of where we were, because in the past we were typically under 20% efficient in converting solar energy into electricity. So that's a really, really big change. And we'll continue to see a lot of different changes. But the important thing to realize is that most metals end up requiring a significant amount of energy to produce. And whether that's through a pyrometallurgical type of process or whether it's through electrolytic, there's still a lot of energy involved. One of the other big challenges that we're facing is that the raw material supply has declining quality. And part of this is our own fault, because what happened was we have scrap that we call obsolete scrap, the stuff that's been in service for 20 or 30 years. And in actual fact, the amount of that will be available will more than double in the next 25 years. So that's a good thing. The bad thing is that it has high residual elements and high levels of residuals. So we're going to have to blend it with some new materials, so some iron ore based materials. We call them ore based metallics. So pig iron, DRI, HBI. And we're going to have to figure out how to blend those in order to be able to recycle all of that scrap that's generated in the next 25 years. At the same time, scrap processors have started to get more and more of this higher residual scrap, and they can't find a home for it. So what do? They stick it in the shredder with high quality scrap in order to produce a material that's sort of not high quality, sort of medium quality, in order to get rid of the material. But that's a big problem because we're contaminating our really high quality material that we don't want contaminated with residuals. So that's a big issue that we're trying to work through. We have evolving raw materials, and we're trying to optimize the use of different scrap types in the furnace, different raw materials in the furnace in steelmaking. And we've actually developed a system that looks at the value in use. So it actually looks at the impact on the value of the product that you produce based on various materials. And then we have major step changes in emerging technologies, digitalization. So there's lots of things happening there. But what you have to realize is that a lot of these things like AI, they don't really work that well unless you start with a good understanding of the fundamentals of a process. So there's still a very large need for process engineers. And sadly, some companies just don't seem to recognize that right now. The other thing is we're developing all sorts of new grades of steel. So we're making steel much stronger. So the weight of steel in a car has dropped by probably 50% over the last 10, 15 years, because we can now make grades of steel that are much stronger, but we don't need as much of it in order to perform the function in the car. So there's lots of things there that are very, very interesting. And some of the typical engineering roles in the steel plant, obviously I'm biased because I'm a process engineer. So I really love studying the process and understanding how to make it run better. But there are all sorts of aspects to this. Mechanical, and that could be mechanical as related to supporting the maintenance and the availability of equipment, or mechanical in the sense of downstream processing of the semi-finished steel into final products, the rolling and so forth. Electrical, obviously that's very important in a lot of these processes, and will become even more important as we move to a steelmaking process route that's focused more on only using renewable electrical energy. As I said, materials, there's all sorts of opportunities there. And not only in sourcing raw materials for the process, but in developing new products, new product materials. Environmental aspects. And what's great here is that over the last 20 years, so it used to be that the production people and the environmental people were usually located at opposite ends of the plant. They tried not to talk to each other. They weren't very friendly. And in the last 20 years, they started to realize that, well, if you understand the process better, then you can actually eliminate some of the environmental problems. And by studying some of the things that you see in gas cleaning systems, you can actually then learn more about the process. So we've actually found that there are synergies now between process engineering and environmental engineering, and they basically come together. So there's just unbelievable number of opportunities, obviously on the computer side of things, on IT, AI. So there are all sorts of opportunities in the steel industry. So hopefully this gave you a really quick overview. It's hard to do this in an hour, but hopefully you saw some things that were interesting, and maybe you'll go and read up on it a little bit more and find out a little bit more about steel making. But you know, steel is going to be here for a long time, and it really presents all sorts of opportunities for engineers. So I think it's something that's I find very interesting. So, and with that, I'll take questions.
Thank you, Jeremy, for a very interesting talk. So I have a question. So how much, if you look at North America, how much of the iron is coming out of a blast furnace now? And, how do nobody's going to put up a new blast furnace, I suppose. So what do we see happening there? Is it going to be natural gas? Going to be hydrogen? What's going to happen?
No, well, what's happened is in North America, we're actually tending to close down the integrated facilities, and we're seeing mergers. So Cleveland Cliffs acquired AK Steel and recently acquired ArcelorMittal North America, with the exception of Dofasco. So yeah, nobody's building integrated facilities in North America anymore. We're building a lot of electric arc furnace facilities, and those are slowly pushing the integrated plants out of business. The really big issue isn't so much the blast furnace as it is the coke plant and the sinter plant. And those two facilities are not environmentally friendly. And so it's very, very difficult, I would say impossible inside North America these days to be able to build a new facility. In China, they've built a lot of new facilities that are integrated because they wanted to build these really large complexes, and essentially the government, because everything's controlled by the government, they weren't restricted. So they moved ahead. But in the rest of the world, we don't expect to see a lot of integrated plants anymore.
The other question I have is on the electric arc furnace. So, there's no good way, as far as I know, there's not a good way to remove copper, right? So,
Yeah,
you can't, the old story is you can't recycle your grandfather's car and make a new car. So how are we going to deal with the impurities in the scrap? We're just going to dilute it with DRI or something. Is that how we're going to solve that problem?
Yeah, but also part of the problem is, so if you look at the steel that's in a car, most of the steel, if you only shredded the steel, your copper content would be like 0.1 to 0.12 weight percent. Instead, it's much higher. And the reason why is we have a lot of free copper. So there's copper bundles, wires, and all sorts of things that are part of that car. And as we move to electric cars, it's going to become even worse, because the amount of copper is going to increase by 3 to 5 times what's in a conventional car. What we need to do is we need to work with the automotive industry in order to make it easier to dismantle a car, easier to recycle and strip out all the copper components, so that what we send to the shredder is just the steel. And if you look at some car companies like Mercedes has had a program for several years now where they actually take cars that have reached their end of life, that still have components which have life left, and they sell these used parts to owners of other Mercedes cars. So it's really only taking that a step further. So there definitely needs to be coordination between the steel producer, the person who utilizes the steel, and then the recycler. So we've got to get all these people together and get a lot smarter about how we do things in order not to contaminate the steel. Now, there are some other processes like cryogenic shredding, where they use liquid nitrogen and they shred, and sometimes there's the ability to process to shred twice, and this helps you remove more of the free copper. People are still looking for that holy grail, some process that would allow you to remove the copper that's contained in the steel itself, but we're still far away from that one.
Well, I think the The copper problem is a thermodynamic one, so it's very hard to beat it because the activity of copper is so low in the iron. It's very difficult to get it out. So I think the objective is to just keep it out, right?
Yeah,
So,
we try to keep it out as much as we can.
yeah.
And as I said, we try not to commingle the steel scrap with free copper. We need to do a better job of separating that. I actually worked with a plant in Turkey. So the plant that I showed you that had that giant furnace, they actually realized that a lot of scrap that they were importing, so Turkey imports a huge amount of scrap from the US. And a lot of scrap that they were getting contained a lot of dirt and a lot of copper. So I worked with them on a program, and they started off, and they hired a bunch of these old ladies to go and pick copper out of the scrap. And what they found was that the money they made from recycling that copper actually provided a profit over the labor to separate the copper out of the scrap. And then they contracted with a company out of Spain and actually installed some equipment that helped them to separate copper and also helped them to separate dirt, because dirt's just a yield loss. It's not bringing anything along. It has no benefit to the steelmaking process. And most contracts specify that the dirt content should be a maximum of 1%. Well, some of the scrap they were receiving in Turkey was up to 7% dirt. So these guys were just scrap processors, were putting dirt in the scrap and selling it for the price of steel, right? So, hey, it's great business if you can get away with it. But I caught them, so they didn't get away with it. So they put in equipment, and the payback on this equipment that they installed was about 3 months. So it was amazing. So I tried to encourage other steel mills to install similar equipment, because it allows you to upgrade the quality of what you're putting into the steelmaking process, which obviously means you're going to have better products.
So, in North America, do you think we'll see more DRI or more imports? So, for DRI, you're going to have to use natural gas or hydrogen. So,
yeah. So in North America, I think we'll see more DRI plants. The limiting factor the last few years in the growth of DRI has actually been the availability of what we call DR grade pellets. And direct reduction grade pellets have a higher iron content and a lower gangue, lower silica and alumina content. Because when you take the pellet and you reduce it in the shaft, you're taking approximately 1.45 tons of pellets and producing a ton of DRI. The silica and the alumina that's associated with the iron ore in that pellet gets concentrated by a factor of 1.5 times. And then when we charge it to a furnace and melt it, that material just forms slag. And so we don't really want to generate that much slag. Because we take a yield loss and also an energy loss. So we try to use higher grade ores to produce those pellets. And there was a shortage a year ago. But now several plants are coming back online. There's a large plant in Brazil called Samarco. It was down for several years. They had a dam burst in their tailings pond. They had a huge disaster. Vale had a similar occurrence last year. So that resulted in a shortage. But now it looks like things are getting back to normal. So then the next thing is, okay, you need access to cheap natural gas. So in North America, we've got cheap natural gas. In the Middle East, they have cheap natural gas. So that's why you see a lot of DRI plants in the Middle East. Europe, no, their natural gas is expensive. So they're probably paying 3 to 4 times the price for their natural gas as we do in North America. So that's an issue. South America, there's potential, but a lot of those natural gas reserves are still getting developed. So we tend to think that we'll see more DR plants in North America and in the Middle East. And then as hydrogen electrolysis becomes more commercial and more efficient, then you'll see hydrogen-based plants in Europe.
I have a question about the electric arc furnaces.
Yep.
So I'm writing a paper right now about like the dust that it produces.
Yep.
When you worked at your plant, did you guys recycle it or did you dispose of it?
Yeah, so what people do is a number of things. If it contains cadmium or chromium, especially chrome 6, it's considered a hazardous waste. And so you have to be very careful about disposing of it. If you do, it has to go into a secure landfill with liner. But if it doesn't contain, and the chrome and the cadmium typically came from things like paint coatings, which are gradually getting phased out. So you actually see now that the level of chrome and cadmium in EAF dust is quite low compared to 10, 20, 30 years ago. At the same time, if the material is high in CaO and zinc, it actually makes an excellent fertilizer. And in fact, there were, so a lot of plants like dust from foundries typically makes its way into fertilizer. So it depends a lot on the composition. And that's partially related to how you run your furnace and partially related to the raw materials that you use in your furnace. The generation rate is typically between 20 and 40 pounds per ton of liquid steel produced. Okay. And the high end of that range would be places that are using very fine fluxes, lime and dolo lime, that a lot of it's getting carried over and carried to the baghouse. So what a lot of people do is they send the material for processing. There's a company called Horsehead. There's another one called Zinc Nacional in Mexico. And what they do is they actually take that material, process it, and recover the zinc. And there was a company that was processing stainless steel dust, but it shut down a few years ago. But it used to produce a ferronickel, ferrochrome type of alloy from the dust. So I don't know, did that help?
Yeah, thank you.
Okay.
What about the fluff now? What are people doing with the fluff?
Yeah, that's a big problem, you know. So first of all, there's more than one kind of fluff in automobiles. So again, this sort of relates back to working with the automobile producers in order to make things to improve the life cycle, right? So now apparently you can separate the two different kinds. They have a slightly different density, so you can use heavy media separation and separate and there's one portion of the material which is okay to burn and the other portion which isn't. So yeah, we just need to do a lot more work and start thinking about a lot of these things with respect to the life cycle to improve the situation.
I think that plant here in Oshawa would be. I think they just bury it on site, I think. Because they can't do anything with it. So,
Well, if you separate it and you get the good stuff, you can actually put that into something like a cement kiln. But then
yeah, maybe,
the other stuff, which I can't remember which one's the higher density. But some of it, yeah, there's not a whole lot you can do with it. But maybe what they should be thinking about is maybe a process to basically dissolve it, put it back in a solution, and regenerate new material or something, you know, which is what they do with tires sometimes now. Some tires actually go back into a process and get broken down and become a feedstock for new tires.
yeah, I always tell this story in my classes. We have this company here. I used to call it Lasco, but they were recycling cars, and they were rated the worst company in Ontario in terms of pollution. But they were recycling people's cars, which was ridiculous. But that's what they did. So
yeah, I spent time at that plant. That was the group, Coast Steel Group. It was part of the Coast Steel Group that was created by a guy named Jerry Heffernan,
right,
who is the inventor of the concept of the mini mill. So his idea was to have a steel plant with an electric furnace, continuous caster, and to produce products to supply into a 500-mile radius. And at the same time, he would also source all of his raw materials from that same 500-mile radius. And that's really how electric furnace steel making started to grow, was through that concept.
So what size are these mills now? We used to call them mini mills, but now they're like maxi mills. So this what, 500,000 tons or?
Yeah, no. There's some of these steel plants now that are electric furnace based. The largest I've worked with produces 3.5, 4 million tons a year from a single furnace. That's the one in Turkey. Several plants here are generating easily between 3 and 4 million tons if they're producing flat products. Long product plants, so plants that are producing maybe rebar or wire rod, specialty bar. Those will typically be probably somewhere between 700,000 and maybe a little over 1 million tons a year. And then you got some of the older plants that are probably in the range of 600,000 to 750,000 tons a year. But those are all long products or structural. Even the structural mills, I mean, the large plants that produce structural steel beams, they're typically 2 furnace shops, and they're producing 2 million tons a year.
Okay, if any people got any other questions for Jeremy, or you can email him later, I'm sure if he's thinking of something, but
Sure.
if not, thank you, Jeremy. It's past 7 o'clock, so it's past my bedtime.
Okay.
So thank you very much for your presentation, and maybe we'll, if we get a chance, we could invite you back again next term.
Yeah,
So
no,
I see,
if you guys are interested, you know, because there's a lot of stuff we can drill down into in this topic as well. There are lots of different electric furnace designs, and I actually teach a class. I've been teaching a class for AIST for 26 years now, on electric furnace designs and optimizing steelmaking operations. But there are so many different areas. Or environmental, I can talk on that. I've worked on a couple of hundred off-gas systems for steel plants over the years. So we're always happy to talk with students and give you some perspective on what's going on. Give you some better insight into the industry.
Okay, have anybody of the people got any questions, comments? If not, I'd like to thank you, Jeremy, for spending your time with us today. I think everybody found it very useful, and I see some chats asking for notes, but I think we have those. So we'll send them to the people who need the notes.
Sure. Yeah, no problem. So,
Okay,
yeah, if you've got questions that are steel related, or even, I also do work in non-ferrous metals, but sort of flip flop. So yeah, if you got questions on something, you can just email me. So,
okay, thank you. Good night.
okay, see ya.
See you again. Take care. Bye.
No
Thank
worries.
you.